everybody. This is going to be a long time coming. This has taken me a few months here. This is the hmrMotionCorrectWavelet, and I'm going to go quite in detail here with the end slide just giving the summary and probably the most useful aspect of it. So the inputs to this function are DOD, which again is the delta optical density, which means you had to have already run the Homer intensity to optical density function to convert your raw data to relative change. The SD is already in the background, and that will be loaded in. It's just, again, the source and detector information. And then the variable that you're going to put in is the IQR, or Inter-Quartile Range. And you're not actually stating the actual Inter-Quartile Range of the data. What you're going to do is be inputting like a weight to that. And typical values are from 0.1 to 1.5. And the smaller the value is, the more noise will be removed, and I'll explain why that is as we go. So the Inter-Quartile Range is basically this little image here on the right. It's the cutoff for Q3 minus the cutoff for Q1. And what you're assuming is, okay, I'm interested in what the middle 50% of my data is, and what you're going to put in as the IQR variable is an adjuster to that. So for this example at the bottom is if your actual data's IQR is 10 and you put into the variable of 0.1, anything greater than 10 times that 0.1, which would be 1, will be deemed an outlier. So you're basically controlling where you're going to assume outliers to be. The lower the value, the smaller the cutoff value will be, therefore the smoother the data will be. The larger the value, the less outliers you're going to claim, and the noisier the data will be. Your output is going to be just the filtered data, which is called DOD wavelet. And this is what the screen would actually look like. So note the default value is 0.1, but the paper that it references, the default is, it suggests a value of 1.5, and it also suggests that a value of 0.1 is likely actually from something called an alpha, which I won't go into any detail because I'm not quite sure what that is. The first step you're going to do is actually normalize the noise, and this is done all in the function itself. And basically what it's saying is that because I assume it's because we're using the IQR, that the noise needs to be based off a standard deviation and therefore a kind of a zero mean value. And so what it's going to do is assume that the standard deviation is that of a normal Gaussian, and it gives you a kind of weighted value here, which is 1.46. In the function, it's 1.4826. It also uses something called a quadrature mirror filter. And again, I won't touch on this. I don't think it's too necessary that you understand this. But it's basically how the filter will be implemented. The process of the normalization gives you the normalized data out. It gives you a coefficient, which is, again, like a scale factor. It gives you the sigma estimated, which is basically that original calculated K value, which I mentioned is kind of based off a Gaussian. And then it's going to multiply that by the mean absolute deviation, which is just a measure of variability, though less common than actual variance or standard deviation. What it is basically the same idea, but more robust to outliers, because you're kind of trying to detect outliers here. So I mentioned I'm not going to touch on the quadrature mirror function, but I want to show you what it is. This is it on the right. That's your input. The output's going to be the normalized data and that coefficient that I mentioned. Just to show you that calculation, when you do the y norm, it's going to be the 1 divided by that kind of Gaussian coefficient multiplied by the data divided by this mean absolute deviation. The sigma, which is that 1.48, is derived from the normal distribution. And the idea is that if you were to set all of your data to 1, what would the deviation be? And you should arrive something like that. So again, kind of like a scale value or a normalization value. Okay, so the coefficient output, again, is basically a scaling factor put onto your data. To give you an idea of what's happening, I just calculated the IQR of raw data that had been convolved, and raw data that was normalized, and these were the outputs. So I show you what the function was, y and c being the actual data, or y norm being the actual data. IQR is just a function in MATLAB. and the outputs being the actual values. So you'll see that they change throughout that. And these only change based on your data. If you change the IQR variable, it's not going to change these values. So you don't really have control over this. And just to show you what this looks like is you'll see the data itself, you can see was altered here quite extensively by a coefficient. So your coefficient was 631, and you can see the y-axis is quite long. I also want you to note that we have zero padding at the end of data. At the end of the data, this will be due to the wavelet filter that's going to be added in shortly. So you do that step for every single channel, and next you're going to apply the wavelet filter. Okay, so we're going to be using the DB2 filter. I don't think you have the option to actually choose which filter you're using. So just to give you an idea, that's the filter right up there in the upper left. The input, again, will be your normalized data. L is the lowest wavelet scale. This basically controls how extensively you will apply the wavelet. So the lower that value, the more wavelets you will apply to the data and the more info you get out of the data. In my opinion, I think that would be like a less smooth version or maybe a redundant version. So it's already hard-coded to 4, so you don't have to really choose that. N is going to be the number of levels that to be decomposed. This has to do with the signal length, and it also has to do with the fact that you zero padded the data. It was zero padded because you're doing log base 2, and it had to be divisible by log base 2, or it had to be a value that 2 to the power of could hit. Okay, so there, in my case, I had 9 wavelengths to use. The reason for this was because it was 2 to the power of 12, and I had a low level of 4. So it's 12 minus 4 plus 1, and it's plus 1 because you have 12, 11, 10, 9, 8, 7, 6, 5, and 4, which is basically 9 total. So you have 9 levels of wavelets that you're going to apply. And these are basically just different resolutions, if you will. So the output is going to be your wavelet decomposition coefficient matrix, which is going to be the time points times the number of levels plus 1, and that's where you get that 9. So you have 9 columns essentially. Okay, so the first step in this is you calculate what's known as D, which is basically the number of times you're going to run this through your data, and that's going to be the N minus L. N being the number of wavelet levels, and L being the lowest wavelet level. So again, 9 will be the value of D. So you actually set up the wavelet, and you then start creating it, and then you begin setting up the remaining wavelets. So again, you're going to have 2 to the power of 0, 2 to the power of 1, 2 to the power of 3, 4, 5, 6, 7, 8, 9, or 8. Each value is the data size divided by n, giving the data downsampled by that amount. And I'll explain what that means in a second here. When you do this, you're going to get 2 outputs at each step. So when you do the first one, you're going to get what's called a approximation and a detail coefficient. So it's 2 values. One is is the low pass, one is the high pass. And at each level, it will give kind of a different weight of each one. As the resolution gets less and less and less, the detail becomes more and more and more, and the approximation becomes less and less and less. And again, you have 9 total of these. And each, as I mentioned, each level is going to be separated into slow and fast components, and it's going to be based off that DB2 wavelet. So the wavelet is, this is actually slightly incorrect. It says the wavelet is compressed or expanded depending on each step. Actually, what the software is doing, this took me a long time to figure out, is it's actually taking your data and downsampling it. And what that means is a value of 100 data points will be compressed to a value of 50. The wavelet itself is actually kept the same size. So what that does is kind of cheat, and it allows your wavelet to kind of be expanded in a way, because it's the same exact size. It's going to be going over the same data, but the data has half the number of steps each time. So the first step, the wavelet is run 2 times on the data, then 4, then 8, then 16, and it continues like that. And you get so many steps on each one. this probably took me the longest to figure out why it was doing this, and it's basically a cheater step of instead of expanding the wavelet, you're compressing the data in a way, but it carries the same function. So as this is done, each of the wavelets moves along, and they're weighted to fit the data. So as they progress through that data, you attach a weight to each one of the wavelets. The wavelets enlarge or shrink based on how well they fit that, and then these coefficients are actually applied to rebuild the data once we process a few things. So again, we had a hard code value of 4 for the lowest wavelet level, and that meant that the data does not model too fine of detail or perhaps redundant of detail, and it prevents the length of the frames, if you will, from becoming too narrow. So if the narrowness of the frame shrinks so low, you're basically doing a half a data point at a time, and you're actually going to not really filter anything. But if you keep the wavelets wide enough, they actually kind of summarize your data a little bit better. So the wavelet analysis basically does this. So this was the default value of 0.1 for the IQR. The original data on the left, you can see, was quite noisy, particularly at the beginning and at the end. And when you apply the wavelet filter, you can see it changes it quite significantly. Whether or not this is an appropriate step, I'm not going to voice an opinion on that, but that you can see what is actually happening. So once that's done, it will actually regenerate the actual signal from that, and you'll see that it is put back in scale with the original. So where we started, back, let's see here, right about here, you can actually see 0.1 about the scale, and we come back here, and we're back down to within 0.1. So it readjusts for the scale when it rebuilds that. So you start with this original filter here, you move it forward, and you arrive at your final signal at the end. You can see that the large peaks have been decreased in amplitude. They've been smoothed quite significantly, and again, whether or not that's correct, I'll leave that opinion to all others. So that's how it works, and again, I apologize for going so deep, but I felt it was necessary, and I hope I got those points correct. But I do want to talk about what the IQR is and how it functions. So what happens if you actually change the IQR? So this was the default. This is what we just did at 0.1. If we adjust to 0.25, you can see that you get a little bit more variety over here. You get a little bit more hairiness on the smooth curves. If you go to 3.5, again, same thing, 5, 6.5, 7.5, 8.5. Okay, that goes to 1. What about 1.5? What about 2? What about 5? What about 10, 50, 100? So at 100, you're essentially looking at exactly the same value. And again, what you're doing is saying anything that lies outside of the original IQR multiplied by this input variable. Anything outside of that, I'm going to dictate as an outlier. Well, if the value is big enough, nothing will lie outside of that, and everything will be included in the data. So as you go smaller, there are more and more and more outliers, and you're removing those from your data before you actually apply these things. So there we go. Here's the small versus the large. You can clearly see a big difference on that. The process summary. The first step is normalization of noise, and this allows the variation to be standardized to a mean value and essentially allows you to look at the IQR appropriately. The application of the wavelet filter, it uses a series of wavelets with differing frequencies. And again, the wavelets themselves don't have differing frequencies. The data has been reacquired, if you will, added by a factor of 2, which changes the wavelet frequency inherently. And then the wavelets are moved throughout that. And then the wavelets are weighted, put through that, and multiplied, and then you actually rebuild the signal through that. The IQR is used to selectively smooth the signal. The larger the value, the less smooth the signal. The smaller the value, the more smooth it is. And again, this filter is used for removing motion and smoothing signal. It's probably not perfect, but it's there. The input variable is simply a tweak to allow you to see how much you feel comfortable removing. And finally, again, the higher the value, the less of the signal you remove, and the lower the value, the more of the signal you remove. Anyway, I hope that was helpful, and if you do notice any mistakes, please feel free to tell me.